Okay, so welcome everybody to the next BU podcast. So I'm Paul Barzensteiner, and with me I've got George Bissias. What I've got you on the show today to talk about is graphene. I mean, if you can just do a little introduction to yourself, how you got onto working on graphene for Bitcoin Unlimited, and then we'll go from there.
Yeah, sounds good. Not to scare you, but I'll go back to like 2010. I was a grad student at UMass working with Brian Levine. I graduated in 2010. I spent a few years in industry, and then I came back to UMass as a postdoc, and Brian and I both got interested in doing blockchain research. And you may or may not know that Gavin Andreessen actually lives in the Amherst area, where our university is located. So we had the idea to kind of get involved with Gavin to come up with a research idea. So, like once a week we would meet and he would tell us some problems in the ecosystem and we would try to get our heads around it. And to be honest, it was going pretty slow. I imagine looking back that Gavin probably was a little bored trying to get these dense researchers up to speed. But he, around that same time, had published this O of 1 block propagation gist that some people might recall. That kind of
Yeah, I think I do remember that.
yeah
That was actually during the kind of block size debate was happening, if I remember correctly.
yeah exactly, and that idea encapsulated in there kind of is the main idea behind graphene. So he kind of threw that out there, and then the fine details came together, as the group kind of worked to refine it. So that's kind of the background, I guess I'd say.
Okay, that's interesting. I didn't know that because I knew that Gavin Andresen was interested and involved in graphene, but I didn't know he had really kickstarted it, and then people like yourself were taking it on and actually tried to work on making it work realistically in the network.
Yeah, I would characterize it like he had sort of that intuitive spark, and we kind of added some things to make it more practical, maybe. And even, he didn't advertise it as being production ready. I mean, he just wrote that gist. So.
Right. Okay. I mean, yeah, that's super interesting. Okay, so it's probably a good point to ask then for people watching, and even for myself. I mean, I know a little bit about graphene, but if you can give a short summary of what graphene is.
Yeah, sure. So it's all about compressing a block size on the wire, so the thing that's sent from one peer to another. And I think at this point it's probably important to point out that it's not going to reduce the block size on disk. It's not going to shrink the size of the blockchain as people sort of imagine it. Yet there are some important reasons to do that, and I guess I'll get into that a little bit later. But I guess the fundamental point of departure from existing solutions or competing solutions like compact blocks, X-thin, and even X-thinner is that those solutions tend to try to reduce the number of bits per transaction in what they send. So they're trying to say, well, by how much can I shorten a transaction ID or something if I'm going to send over an entire list of transactions that are in the block? And so some pretty impressive improvements have been made from compact blocks down to what I think X-thinner is actually, as far as I've seen, the best compression for doing per transaction compression. Graphene looks at things much more differently. It sort of starts with the gestalt and says, all right, most peers have largely the same transactions in their mempool. The mempool is just sort of pending transactions. And then when a miner creates a block, he or she tends to take all the transactions in the mempool and make a block out of it. So if you and I basically have the same set of transactions in our mempool, and we know that a block just came out and it has pretty much all the transactions from the mempool, then I shouldn't, from an information theoretical standpoint, I shouldn't have to really communicate a certain number of bits per transaction. I should be able to just kind of give you the delta. Take everything in your mempool, and by the way, let me just fill in the cracks. There might be some, differences, some issues that arise. So that's what graphene is trying to do. It's really trying to just communicate the differences between mempools and blocks and mempools.
Okay, yeah, that was a really good summary of what graphene is. So maybe the next most important question is, what's the benefit of this? Why would you need to compress the amount of information that you're trying to, spread across the network, propagate across the network?
Yeah, so I guess I would say there's why and there's also when, because graphene's not always going to be useful, for all blocks or all situations. So the why is really about speeding up block propagation. And, at this point I should say it's not that compression, absolute size of bits being transferred, that's not the only determinant of propagation speed. And, people have pointed this out in the past. There's also things like the number of round trips that you're sending. So currently graphene does use, say like 1.5 round trips, whereas some protocols can just use 1. And so there are certain aspects that are not just about number of bits. But if you accept sort of the simplification that we're really looking to shrink the number of bits, which certainly should come into play for propagation speed, then the next question is, why do we care about propagation speed?
Right, exactly.
The big reason is, it cuts into the orphan rate. So you imagine that, let's say I produce a block and I want to communicate it to you. You're also a miner. The instant that I've created that block, you're not aware of it and you continue to mine. And if it takes me 15 seconds or a minute to communicate my block to you, and you produce a block in that same intervening time period, then we're going to have a block race. Both of us are going to be competing to get our blocks accepted. And I think, I won't go into why this is undesirable. I think most people recognize that, at least from a mining standpoint, miners aren't happy when their blocks get orphaned, and it leads to some inefficiencies in the network. So that's like one reason. And there are two other reasons that kind of play off of this orphan rate. I think Peter Risen did a really good job in his subchains paper of characterizing what the cost to a miner is per bit added to a block size. So what he did is work backwards from this notion that, if you have to transmit so many bits over the network in order to get this block propagated, and for every, let's say there's a certain amount of time that elapses for every bit that you send, and there's a certain, based on the exponential distribution, there's a certain probability that another miner will mine a block during that, those seconds that accumulate during your transmission, and the block subsidy is so much, in fiat terms, then a miner's cost to adding more transactions to the block, increases by so much as you increase the block size. And so at some point, even though there is some marginal increase in reward for adding transactions, at some point that marginal cost becomes too great. And so miners sort of, even if you make blocks as large as possible, you take that block size limit all the way to infinity, miners still will not be incentivized to pack those blocks full of transactions. And there's also this weird thing that, related to the orphan rate. Like, imagine I'm a miner and I control 99% of the hash rate. All of the blocks that I produce, none of those will be orphaned, right? Because I have instantaneous propagation speed among all of my miners, my mining nodes. And then for the 1% miner, they're sort of going to incur the highest orphan rate risk because they have, sort of 99% of the hash rate is competing against their 1%. So obviously that 99% miner, if there's a block race between the 1% miner's block and the 99, he's going to go with his own block. And so the end result is that if you allow for large orphan rates, then you sort of marginalize those 1% miners, and it can lead to an incentive to have more mining centralization. So that's
right. It's one of the centralization pressures that are caused by
exactly. So that was sort of a long way of saying like why we want to use graphene, and then the other thing that I wanted to address is when. I think these aren't hard and fast numbers, but just from looking at the data and from a couple different sources, I would say if you have fewer than 100 transactions in a block, a good rule of thumb is that probably a full block is going to be smaller than Graphene. And if you have, let's say, up to 250, I think it's probably even a bit lower than this, but just to be safe, if you have up to 250 transactions in a block or fewer, then it's even better to use like compact blocks, X-thin, or perhaps X-thinner. Maybe X-thinner is the best of those three. So the regime where you would want to start using Graphene would be like 250 transactions and more. And then we can start to talk about sort of asymptotic bits per transaction. And it turns out that Graphene, it's a little bit more complicated than that because Graphene has a dependence on the size of the mempool in addition to the block. But even if the mempool is, say, like 5 times the size of the block, Graphene still asymptotically will use like maybe 3 to 4 bits per transaction, as opposed to X-thinner, which would be kind of the most, the highest compression of the alternatives uses around 12 bits. So I think Graphene has the best, as far as I know of, asymptotic compression. And I think Jonathan Tumim has been pretty, generous in his assessment of Graphene. I think he's been pretty honest in how he stacks up against, X-thinner against Graphene. And I think he would say, it's the intent of X-thinner is not to replace Graphene, but more to use as a failover. And then also he has this sort of swarming protocol block torrent that X-thinner is designed to work with. So I do kind of think that most people would agree that asymptotically Graphene has some advantages in terms of block size.
So basically, it works best at scale.
Absolutely, yeah.
Right. Okay, that's interesting. That's something I didn't know about. I just assumed that it works best.
Would always be better. Yeah,
block sizes.
There are trade-offs for sure.
Mm-hmm. Okay, that's interesting. So, I haven't checked recently. I don't know how many transactions per second we're getting on Bitcoin Cash at the moment. Do you know if Graphene would be best to use already right now with the number of transactions there are?
I haven't looked in the very recently. I would say that on a day-to-day basis, it's not absolutely necessary. I think that it's something like you could use compact blocks and get comparable performance. So I think it's more about getting us ready for that next stage of growth.
Right, that makes sense. This is really fascinating. I don't know if this is going to be too technical for people, but I personally would be super interested to learn how this works, like on a technical level. I understand like the use for it, but how you actually manage to get that level of compression compared to X-thin or compact blocks or any of the other compression technologies.
Yeah, so it's kind of, I suppose it's easiest to explain when you've got like some slides up and some Venn diagrams, but I can wave my hands around a little bit to try to explain to an intuition. Yeah, for sure. So let's go back to Gavin's gist about O of 1 block propagation. O of 1, for people who aren't computer scientists or whatnot, is basically saying it's constant in the size of the block. So what Gavin...
It's like linear scaling, right?
Not even linear.
Okay, not even linear.
It would be a fixed size and not grow at all. So you could have, I'm going to dismiss this idea momentarily, but the thing that got Gavin excited initially was that maybe I can just send a small amount of data, like 100 bytes or 100 bits per block, no matter what the block size is, that allows the sender and the receiver to reconcile sets of transactions in the block. So this would be like, this amazing thing. And so the intuition behind that is as follows. Gavin discovered this, at the time, kind of arcane data structure called an invertible Bloom lookup table that was fairly new. It's an IBLT for short. And what this data structure does, it's fixed size, so hence the O of 1. And what happens is, so I'm a sender, I'm sending a block to a receiver. So what the sender does is he packs transactions into this IBLT, and actually he's going to pack their IDs, not the transactions themselves, but I may just say transactions. So he packs them into this IBLT, and the IBLT only can hold, only has the space to hold enough room for like 10 transactions, okay? But The neat thing about the IBLT is he could put 10 million transactions in there and it can accommodate them. But it still only has enough space for 10, which is bizarre. But he sends that over to the receiver. Receiver takes that IBLT and she creates her own IBLT. Now, he put all the transactions from the block. She doesn't know exactly what's in the block yet, so she just puts everything in her mempool into her IBLT. So what you have here are these two data structures. One contains exactly what's in the block. The other contains exactly what's in the receiver's mempool. So if you go back to what I said earlier, this notion, Graphene sort of latches onto this notion that mempools are basically in sync, and blocks, when a miner creates them, basically contain everything in the mempool. Okay, so to the extent that all those assumptions are perfectly true, then the sender's IBLT with the block and the receiver's IBLT with the mempool, they're exactly the same. Okay, maybe they're off by like 1 or 2 transactions. So what the IBLT allows you to do is take what's called the symmetric difference of these two sets. So basically you subtract them. It's sort of a symmetric subtraction. And the result that you get out, it'll have 2 lists. One list will say, this was stuff that was in the sender's IBLT that the receiver didn't have. And this is stuff in the receiver's IBLT that the sender didn't have, meaning this is just garbage, right? So on one hand, the receiver might have had, a couple extra transactions in her mempool. Those will get discarded. On the other hand, she may have been missing some transactions that actually were in the block. She can grab those from the sender's list. And so this is the amazing thing about IBLTs. You could start with 10 million transactions on the sender side, 10 million on the receiver side. As long as the symmetric difference was 10 or few items, then the IBLT will be able to quote unquote decode and give up those 10 transactions that were different between the two of them. So where this kind of breaks down, there's a few different things. One kind of basic thing is like, how do you know how out of sync the sender and the receiver are? So how do you know how big to make this symmetric difference? And that's something that we've sort of worked to refine over time, not just in the research paper, but also in the implementation of Graphene. There's sort of like initially the receiver sends the sender the size of her mempool. So the receiver can say, whoa, that's either they exactly match my mempool and hers, or they're totally different, and he can know, okay, we need to like pad this IBLT to be much larger to accommodate more differences. But there's another issue, which is that, in general, yes, it's true that miners will try to, scoop up as many transactions as they can in the mempool, but in practice, this doesn't actually happen. So there are definitely times when not all the transactions make it into the block for whatever reason. And like, it can be a large number. And so Gavin's solution, just using an IBLT, this would require that you pad out the IBLT with maybe 1,000 transaction IDs. And the problem with IBLTs is they're not incredibly efficient at just sending a transaction. Let's say the overhead associated with sending a transaction in this format is approximately 1.5. So what that means is that if a cheap hash for a transaction is 8 bytes, then the IBLT is going to have to use 12 in order to send it over. And so the first innovation of Graphene over Gavin's gist is to say like, well, maybe the receiver can filter out some of the transactions in her mempool before she even assembles her IBLT. Okay, because now let's imagine a scenario where we have 1 million transactions in the mempool of each, but there's only 100 transactions in the block. All right, so what the sender is going to do now is he's going to send the IBLT with those 100 transactions, and he's also going to send a Bloom filter with those 100 transactions. And a Bloom filter is a related data structure that just allows you to take, so the receiver on her end has her 1 million transactions and she has her Bloom filter. She's going to pass those 1 million transactions through the Bloom filter, and the Bloom filter will say, yes, this one's in there, no, this one isn't. And it'll allow her to sort of winnow down that large 1 million transaction set down to, let's say, 150 transactions. And so the trade-off, all of these data structures have trade-offs. They're probabilistic data structures. The trade-off with the Bloom filter is that it has a certain false positive rate. So if you test 1 million transactions and actually like 100 of those transactions are true positives, should actually be in the block, it'll return 150. So there'll be like 50 crufty ones that you can't handle. And so the idea with graphene is like, all right, you use these things, chocolate and peanut butter, you use them together, the IBLT will compensate for the false positives introduced by the Bloom filter. Okay, so I've said that there's a certain overhead for the IBLT. For every transaction it has to recover, you need an extra 4 bytes, say, to recover that. And then we also have this false positive rate of the Bloom filter. The Bloom filter itself is also going to take up some space. Okay, so the trick that we do in the graphene paper is to say like, all right, well, let's trade off between these two data structures in terms of size and figure out how big of an IBLT relative to the Bloom filter should we create in order to minimize the total size between both data structures. And that's it. So how technical was that? A little too technical?
That was pretty technical, but you explained it very well considering you don't have any slides or anything to show.
I apologize if that's not super clear, but that is...
No, that's very well presented.
That's essentially the, sort of version 1 protocol. And I'll just say that there are lots of little details. And again, these are probabilistic data structures, so they fail with some probability, and version 2 came along to try to adds a whole different leg to the protocol to try to compensate for these failures.
So is that something you're working on now then?
No, so version 2 is complete. It's
great.
Been in the BU release probably almost a year now, perhaps a little longer. Another thing that I want to mention is like the fundamental set differencing logic for graphene is not unique to block propagation. So it can be used for other things in Bitcoin Cash. One of them has actually also been deployed, which is called mempool sync. And so again, you have like sets of transactions in a mempool, and perhaps you want to just synchronize the set of transactions on the sender with a set of transactions on the receiver. The reason for doing this obviously is that, well, there's lots of reasons, but the first reason is that if you're going to be doing graphene works best with synchronized mempools, so you can sort of preemptively synchronize them by passing a graphene data structure back and forth and keeping those up to date. I think we do it every 30 seconds now. You can do it much more frequently. And another reason is that...
Sense.
What's that?
That makes sense. Like, so you're, instead of having a larger difference at the end when you need to send that block, you've got a smaller difference at the end by syncing earlier on.
Exactly, right. Yeah. And another thing is that you may be aware that there's a huge amount of wasted overhead in communicating transactions between full nodes because the number of inventory messages sent network-wide for any new transaction is on the order of the number of edges in the network. So if each node has 8 to 50 links, outgoing links, then that inventory message is going to be sent along n nodes times 8 at least different edges. And so what we can start to do is dial back the number of inventory messages that are sent by nodes for new transactions, and maybe only send like a randomly chosen subset of those, and then supplement with mempool sync every 5 seconds or something like that, so that we sort of do more bulk transfer in addition to some direct transfer of transactions.
Okay, so that would be not when a block is propagated.
This is in between.
Like, just with transactions passing
yeah.
between the nodes. Okay.
Exactly.
Mm-hmm.
And then I'll mention one other thing, which is a little bit of a sales pitch, being this bobtail work that we've been doing, combining that with Storm. We have something called a subblock, and really Ameni was interested in using this even back in the days when he was working on weak blocks. Any type of, it doesn't have to be the regular block that we use. Any collection of transactions can use the graphene technology, if you will, to reconcile sets. And so we're actually using that in our bobtail Storm implementation to shrink the size of these sort of subblocks that are passed between peers.
Oh, right, yeah. I mean, we won't get into this in too much detail, because I would like to, if you have time at another point, that you could come on and talk to everyone about Tailstorm or Bobtail and Storm that you're working on.
Happy to.
But yeah, so just to quickly cover what that is, that's a technology, well, it's two technologies combined together. One that aims at stabilizing the variance in block time. Is that correct?
Yep.
and the other one is to it's a technology to maybe it's better if you explain it. So it's
Sure.
yeah.
Yeah.
If you go ahead and explain the other part of the technology.
Yeah, so it's right now I guess this would be derailing our conversation a little, so I'll make it very brief. But
Right. Yeah.
basically, you have one proof of work sample per block currently. It's the one hash that fell below the target. In Bobtail, if you have more than one, you use multiple pieces of partial proof of work. You can both reduce the variance in the block time as well as reduce your susceptibility to double spend and selfish mining attacks. In fact, it virtually eliminates the risk from both of those. So that's a benefit of Bobtail, but it doesn't do anything about zero confirmation. It doesn't care or say anything about what happens in between the 10 minutes in between blocks being generated. Storm, on the other hand, is something where lots of partial proof of work is passed around between nodes and between blocks, and that can be used to do things like provide evidence of double spend or evidence that you're not being double spent, and provide some probability that your transaction will ultimately be confirmed. Unfortunately, the incentive structure isn't quite in place under Storm because miners don't really have much incentive to share their partial proof of work, and in my opinion, under Storm alone, they're actually incentivized to withhold it. So by marrying the two technologies, we sort of are aiming for having both the pre-confirmation, pre-consensus, some probability that your transaction will be confirmed, and also getting sort of the robustness of multiple confirmations of strong blocks with Bobtail, lower double spend, susceptibility, etc.
Right. And getting quicker confirmations.
Yeah,
More
so
stable
so they'll still come out in 10 minutes on average, but it'd be very unlikely. I think it's like 95% of the time they'll come out in 12 and a half minutes or fewer.
Right. Instead of sometimes you have to wait 50 minutes, an hour, or
Exactly,
longer for a
yeah.
confirmation. Mm-hmm.
And so can I?
Okay, yeah. I mean, again, like I don't want to dive into that too much.
Yeah,
'Cause
yeah.
I'd really love to have you come and talk
Absolutely,
about that in more
it's
detail
not
another
really
time.
relevant here, but I want to add one more caveat to the technical description of graphene, which is that there are ways to mix and match components in graphene. So like we use IBLTs for set reconciliation, but after the fact, it's sort of come out that maybe there are better data structures to use instead of the IBLT, like some like CPI sync are sort of drop-in replacements for IBLTs that do not fail, don't have like a failure rate associated with them. So that's not something that our group has looked at in detail, but I just want to say that there probably are some micro, or maybe they're not so micro, but there are some improvements that could be made over time to the protocol.
And is that something you intend to do? Like, let's say maybe after you're done with the
Yeah, I mean, time permitting, sure. I mean, there's kind of a list of things that I wouldn't mind improving in the protocol.
Okay, interesting. So I mean, I guess this definitely brings us to how obviously this is already implemented in BU Graphene version 2, as you said. That's different to it being widely implemented across the whole Bitcoin Cash network. So what do you feel needs to be done to make more use of this, for Bitcoin Cash to make more use of this technology?
Yeah, it's a good question. This is probably the area that I'm weakest in that I don't have a large amount of contact with developers and other implementations of Bitcoin Cash, and I've not been part of an effort to port features between implementations. So I can probably give you an unsatisfying, series of answers that kind of relate to what I do know. So I don't know how hard it is. For example, I know that Griffith spent, several months trying to get X version ported to, BCHN and some other implementations. So an X version is like, on a technical level, is pretty small compared to Graphene. So in terms of getting everybody on the same page, there could be like a large, let's say, social effort to get everybody to agree on the spec and whatnot. But I can say for sure, some things that Graphene has going for it, like it does not require a hard fork or any kind of fork. So it's something that can be implemented as an option for miners. Across implementations. there, that said, it is like a fairly complex protocol. You might have gotten that sense from my description. There are a lot of like edge cases to consider and whatnot. But there is a spec, and it's been kept up to date. It's on the, if you go into the BU main repository, it's under the doc folder, and you can see the various versions of Graphene that have been, those spec versions have been updated. And the non-trivial data structures like our Bloom filter implementation and our IBLT implementation, those also have specs for them. So that effort has been started. I would say realistically, and we've tried to engage the community throughout, and I have received feedback. It's a funny thing because sometimes you get feedback, and let's say I've addressed like 50% of it, and then the other 50% is like we have a discussion among some of the other devs at BU, and we're not quite like we don't necessarily agree with the suggestions. So there would, I haven't made all the changes that were suggested, so I think there would have to be, realistically more of a conversation among developers and different implementations about how they wanted to like move forward, whether or not they actually want to solidify around the spec as it is today. So
Right.
I think
And,
some effort is
obviously,
necessary.
Yeah, I mean, that makes sense. I mean, I guess obviously at the moment, given the current situation within Bitcoin Cash, it's probably the situation that right now, obviously most, not all, unfortunately, but most teams are trying to collaborate as best as possible. And so to start that process, because it's been somewhat dysfunctional over the last couple of years, to restart that process again, the low-hanging fruit are being taken to try and find commonalities to how we can add new features to the network. And maybe Graphene is not at the top of the list because it is something a little bit more complicated to implement.
Yeah,
so
I
hopefully,
can understand that.
Yeah, I mean, hopefully, when things settle a bit and we're past the upgrade coming in November, then there may be space for each of the teams to start thinking about how Graphene could be implemented.
Yeah, and I would say also like there's one aspect of the Graphene protocol that I think has been controversial. Let's not say like a huge controversy, but like Omri had a problem with this, I know, and I think maybe others have mentioned it, and I sort of agree, which is that there's this first leg of the protocol where the receiver is required to tell the sender how big her mempool is. And that allows us to do this calibration with the data structures. And so the thing that's unfortunate about that is that it eliminates the possibility for what in Bitcoin for compact blocks was known as high bandwidth mode, and in BU is known as expedited mode. And in expedited mode, basically, you're able to, as soon as the sender receives a block, if the receiver has marked him as an expedited, intermediary, then that sender can immediately send her the block instead of her asking for it. And so when you do that, you can't really do that in Graphene currently because you need some information from the receiver first. And so one thing that I think an improvement that could be made to Graphene, which I think on a theoretical level is definitely possible, is to remove that first leg where the receiver communicates the size of her mempool. And I think if we can get rid of that, then it would make it sort of more palatable to people from other implementations. What's necessary there is wide-scale deployment of the mempool synchronization, so we can sort of have an accurate guess of what the receiver's mempool size would be, and then also just a little more research and testing to validate that we can accurately guess that mempool size.
Okay, that's really interesting. So there is still plenty of room for improvement, even to satisfy some of the other requirements that people have asked of Graphene.
I think so. I mean, I guess, I think in the spirit of academic openness, definitely there are things that can be improved. It won't change the asymptotic performance of Graphene. If you're sending a 1 megabyte versus a 100 megabyte block, like let's say you're saying a 100 megabyte block, that first round trip that sends the receiver's mempool size is going to be completely dwarfed by the time it takes to send, even the compressed version of that block. So
right, so it may only be relevant now in this small box, but
yeah.
it wouldn't be like even consideration later on. Maybe
that's my opinion, yeah. But we don't have huge blocks right now, so no. I think to make it more palatable in the short term, that's a reasonable concession.
Okay, yeah, that's interesting. Do you feel there's any other details to graphene that you feel people should know about? That we haven't covered in the call so far?
Not really. I think I covered most of the important ones that I can think of.
Yeah, I think you've done an extremely good job of explaining graphene, considering
Thanks.
The level of technicality and understanding it. That's a very, very good explanation of how it works. So yeah, I want to thank you obviously for coming on the show and explaining to me and to everyone how graphene works. I really hope that other implementations can take the work of the other people who've developed graphene and get that working on the Bitcoin Cash network, because obviously we as a network was essentially founded on the basis of scaling Bitcoin, and graphene seems to be one of the key technologies in doing that. So yeah, thank you again for coming on the BU podcast and explaining that.
Yeah, absolutely. It's been my pleasure.
Yeah, and again, I really, if you have time at another point, I'd really love you to come on and discuss Tailstorm with everyone to explain your work on that.
That'd be great. Yeah, I'd like to do that.
Excellent. So yeah, thank you everyone for watching the BU podcast. As always, please subscribe for more interesting content like this in the future. Like the videos, go follow the Bitcoin Unlimited Twitter at bitcoinunlimited on Twitter. Yes, keep watching for more videos soon. Thank you, George. Take care.
Thank you.